right now on some fault line inside some stock exchange. And inside your own chest, the same quiet process is running. And all three of them end the same way. Here is what I want you to sit with before we start. Why did a quake a pacifist? A man who destroyed his own research rather than let it help kill a single person. Spend the back half of his life measuring human wars with the exact same ruler a seismologist uses to measure earthquakes. What does the shape of one grain of rice have to do with whether a financial system collapses without warning? And why does the rhythm of your own heartbeat carry the same fingerprint as a solar flare 93 million miles away? Those are not three questions. They are one question wearing three disguises, and the answer is a single straight line that almost nobody has ever put in front of you. A line that already contains the next catastrophe. Its size, its near certainty, everything except the day it arrives. Get comfortable, and if you are not already there, subscribe or join while you are here. If you want to follow this kind of thing further, the Patreon goes wider and deeper into the same territory: physics, deep time, collapse, and the math sitting underneath all of it. Stay with it to the end, because by the time we reach the bottom, you are going to understand why the long calm you are living through right now is not the absence of the catastrophe. It is the catastrophe being built, quietly, one grain at a time. Let's begin. There is a single straight line that contains the worst things that have ever happened to the human species, and almost nobody has ever shown it to you. On the morning of the 1st of November, 1755, the ground under Lisbon tore open, and somewhere between 30,000 and 50,000 people died in about 10 minutes, some in the shaking, more in the sea that came afterward, the rest in the fires. On the 19th of October, 1987, the American stock market lost more than a fifth of its entire value in a single trading day, and not one economist, then or in the almost 40 years since, has been able to point to the thing that caused it. On the 14th of August, 2003, a few power lines in Ohio sagged in the summer heat and brushed some overgrown trees. And within about an hour, the lights went out for 50 million people across 8 American states and the province of Ontario. And then there is the Second World War, which killed somewhere north of 60 million people and rearranged the entire planet. A volcano of dead in Portugal. A day of vanishing money in New York. A cascade of darkness across the Northeast. A war that swallowed a generation. You would think these were 4 completely different kinds of event, 4 separate catastrophes with 4 separate explanations related only by the fact that they were all bad. They sit on the same line, the same equation, and the equation does not think a single one of them is special. That is the part you were never told, and the reason you were never told it is not that it is fringe, and not that it is unproven, and not that it is some lonely theory clinging to the edge of respectability. It is published. It is peer-reviewed. It has been sitting in the physics literature since 1987 and in the seismology literature since the 1940s. The reason you were never told it is that the implication of that single line is so uncomfortable that the people who understand it best would rather talk about almost anything else. Because here is what the line says. It says that the size of the next catastrophe is already decided, not by fate, not by God, not by anyone watching over us, by mathematics. The frequency and the magnitude of the disasters that are coming for you, for your money, for your city, for your species, are fixed by the structure of the systems you live inside, in the same way that the odds of a coin are fixed by the fact that it has 2 sides. The math can tell you with something close to certainty that a catastrophe of a given size is coming, and roughly how often catastrophes of that size arrive over the long run. What it cannot tell you, what it will never tell you, what it actively forbids you from knowing, is when. I want to be precise about how strange that is, because the strangeness is the whole point, and if I rush past it, the rest of this will sound like a metaphor, and it is not a metaphor. Start with earthquakes, because earthquakes are where this was first measured, and the men who measured it had no idea they were about to find a pattern that would turn up everywhere, from the stock market to the extinction of species. In the 1940s, at the California Institute of Technology, two seismologists named Benno Gutenberg and Charles Richter, the same Richter whose name you already know from the scale, did something that sounds boring and turned out to be one of the most disquieting discoveries in the history of science. They counted earthquakes. They took every earthquake they had records for, sorted them by magnitude, and asked a simple question: how many big ones are there compared to small ones? What they found is now called the Gutenberg-Richter law, and you can write it on the back of a receipt. For every step up in magnitude, earthquakes get about 10 times rarer. There are roughly 10 times as many magnitude 5 earthquakes as magnitude 6 earthquakes. There are roughly 100 times as many magnitude 4 earthquakes as magnitude 6 earthquakes, 1,000 times as many magnitude 3s. The relationship holds across the entire range, from tremors too small to feel, up to the ruptures that move coastlines, and it holds almost everywhere on Earth, and it has held for as long as anyone has been able to measure it. Now here is why that is not boring. A straight line on this kind of graph, and it is a straight line, means there is no such thing as a typical earthquake. There is no natural size for an earthquake the way there is a natural size for an adult human being. If I picked 1,000 grown men at random, they would cluster tightly around 5 feet 9 inches, and I would not find one who was 1/4 of an inch tall, and I would not find one who was the height of a skyscraper. Human height has a characteristic scale. It has an average that actually means something, and the extremes are so rare they may as well be impossible. Earthquakes have no characteristic scale. There is no average earthquake. The same physical process that produces a tremor you sleep through produces the rupture that kills 250,000 people, and the process does not know at the moment a fault begins to slip which of those two things it is about to become. Think about what that actually requires. When a fault deep in the crust starts to give way, the rock begins to slide. Sometimes it slides a few centimeters and stops, and you get nothing. A microquake registered only by instruments. Sometimes it slides for a few meters along a few kilometers of fault, and you get a quake that cracks plaster. And sometimes, with no warning and no difference in how it began, the slipping does not stop. It cascades. One section of fault failing loads the next section past its breaking point, which fails and loads the next. And the rupture runs for 100 kilometers, 500, in the largest events more than 1,000. And a city dies. The terrifying thing the Gutenberg-Richter law is quietly telling you is that the small quake and the catastrophic one are the same event. They begin identically. The only difference is how far the cascade runs before it stops. And nothing in the initial slip determines that. The earthquake decides how big it is going to be while it is happening, and not one instant before. This is the first thing I need you to sit with, because everything else in this story is going to be a variation on it. The catastrophe is not a different kind of thing from the everyday. It is the everyday run to its extreme, and the extreme is built into the math. So if you wanted to predict earthquakes, and people have wanted this desperately for obvious reasons, you would want to find the difference between a fault that is about to produce a magnitude 3 and a fault that is about to produce a magnitude 8. And the single most expensive, most carefully designed earthquake prediction experiment ever attempted was built to find exactly that, and I will tell you now that it failed so completely that it more or less ended the field. But I am getting ahead of myself, because the failure of that experiment is not a story about not trying hard enough. It is a story about the prediction being mathematically impossible. And to understand why it is impossible, you have to leave earthquakes entirely and look at a pile of sand. That is not a figure of speech. In 1987, 3 physicists sat down and built a pile of sand inside a computer. And that pile of sand explained the earthquakes and the wars and the crash of 1987 and a great deal else besides. It is one of the most cited ideas in modern physics. The man behind it died at 54, abrasive and largely unsatisfied, convinced he had found the way nature works, and equally convinced that most of his colleagues were too timid to admit it. His name was Per Bak, and the reason his pile of sand should disturb you is not that it is complicated. It is that it is simple, and it still cannot be predicted. And if a pile of sand on a table cannot be predicted, then neither can the things that pile of sand turns out to describe, which includes, and I'm going to spend the next 2 hours earning this sentence, the civilization you are currently living inside. Per Bak was born in Denmark on the 8th of December, 1948, and by every account of the people who worked with him, he was one of the most difficult and one of the most brilliant physicists of his generation. And those two things were not unrelated. There is a line about him from the physicist Predrag Vitanovic that gets quoted because it is perfect. He said Bak was the most American of Danes. Danes, he said, avoid confrontation. Bak was arrogant and loved to fight with his colleagues. There is a story, and it is on the record, of Bak sitting through a young researcher's conference talk and then announcing to the room, when it was over, that perhaps he was the only crazy person there, but that he understood zero, and he meant zero, of what had just been said. He said it to the speaker's face, in front of everyone. The New York Times obituary, when he died, called him intellectually pugnacious, which is the kind of phrase you reach for when you are trying to be polite about someone who was not. I tell you this not as gossip, but because the abrasiveness and the idea are the same thing. Bak believed he had found a single mechanism underneath an enormous range of phenomena, and he was constitutionally incapable of the hedging and the qualifying that the rest of his field used to make big claims socially acceptable. His friend, the physicist Lee Smolin, once described the way Bak thought about the world. A tree on fire, Bak would say, is like a person with the flu, is like a galaxy forming stars, is like a gene switching on, is like a trader placing a bid. To everyone else, these were different subjects, studied in different buildings by people who never spoke to each other. To Bak, they were the same equation wearing different clothes, and he was right often enough and obnoxious enough about it that he spent his career being simultaneously celebrated and resented. Here is the pile of sand. I am going to walk through it slowly because the whole argument lives in the details. And if you skip the details, it collapses into a slogan. Imagine a flat grid, like a chessboard, except it can be any size, and in the real simulations, it was often quite large. You drop grains of sand onto the squares of this grid, one at a time, choosing squares at random. Each square can hold a certain number of grains before it becomes unstable. In the standard version of the model, the magic number is 4. As long as a square has 3 grains or fewer, it just sits there. But the moment a square reaches 4 grains, it topples. When it topples, it gives away all 4 grains, one to each of its 4 neighbors, north, south, east, and west, and it goes back to empty. And here is the only interesting thing in the entire model. When a square topples and hands a grain to each neighbor, those neighbors now have one more grain than they did, which means a neighbor that was already sitting at 3 is now sitting at 4, which means it topples 2 and hands grains to its neighbors, which might push them to 4, and so on. One toppling can trigger the next, which triggers the next. A single grain dropped on a single square can set off a chain reaction that spreads across the grid. That chain reaction is called an avalanche, and the entire point of Per Bak's career is contained in what those avalanches do. You drop grains one at a time and you watch. At first, nothing much. The pile is mostly empty. Grains land and sit. Occasionally, 2 or 3 squares shuffle a few grains around. But as you keep adding sand, the grid fills up. More and more squares are sitting at 2 or 3 grains, primed, 1 grain away from toppling. The whole system gets tenser, and then you reach a state and the system reaches it by itself, where the pile is balanced right at the edge. Add 1 more grain almost anywhere and something happens. Usually something small. A couple of topples and it settles. But sometimes, with no warning, that 1 grain sets off a cascade that races across the entire grid, toppling thousands of squares, an avalanche that involves a huge fraction of the whole pile. Now you do what Gutenberg and Richter did with earthquakes. You run the model for a very long time, you record the size of every single avalanche, and you ask how many big ones there are compared to small ones. And you get the same straight line. The avalanche sizes follow a power law. Small avalanches are common, large ones are rare, and there is no characteristic size. No typical avalanche. The pile produces tiny shuffles and grid-spanning collapses from the exact same rule, dropping the exact same grains, and there is no special grain and no special moment that produces the big ones. Read that last part again, because it is the thing that should genuinely unsettle you, and it is the thing that took me a while to absorb. The grain of sand that triggers the catastrophic, system-spanning avalanche is identical to the grains that did nothing. It is not bigger. It is not dropped harder. It does not land in a special place that you could identify in advance. At the instant you release it, it is indistinguishable from the millions of grains that landed and simply sat there. The difference between the grain that does nothing and the grain that brings down the whole pile is not in the grain. It is in the state of the pile when the grain arrives, and the pile arranged itself into that state on its own, with no one tuning it, simply by being fed 1 grain at a time. This is the discovery, and Bak gave it a name that is worth stopping on. He called it self-organized criticality. Criticality is a word physicists use for a system poised exactly at a tipping point, the knife edge between 2 states, the way water sits right at the boundary between liquid and steam at exactly 100 degrees. Normally, to get a system to that critical point, you have to tune it carefully. You have to set the temperature to precisely the right value, hold the pressure at precisely the right level. Criticality is supposed to be a delicate, special condition that you have to engineer. What Bak and his 2 collaborators, a physicist named Chao Tang and a physicist named Kurt Wiesenfeld, showed in their 1987 paper, published in the journal Physical Review Letters, was that the sand pile tunes itself. It drives itself to the critical point, and then it stays there. Nobody sets the dial. The system finds the knife edge on its own and balance is there forever, perpetually poised on the edge of a collapse that could be tiny or could be total. The title of that paper, and I love this title because it sounds like it is about something small and technical, was Self-Organized Criticality, an explanation of 1/F noise. 1/F noise, sometimes called flicker noise or pink noise, is a strange statistical signature that shows up in an absurd range of places. In the hiss of electronic circuits, in the flow rate of rivers, in the rhythm of your own heartbeat, in the brightness fluctuations of stars, in the loudness variations of a piece of music. For decades, nobody had a general explanation for why this same fingerprint appeared in such wildly unrelated systems. Bak's claim was that 1 over F noise in time and fractal structure in space are the two visible signatures of a system that has quietly tuned itself to criticality. The pink noise in your heartbeat and the fractal branching of a river delta and the avalanche statistics of earthquakes were to Bak 3 faces of one phenomenon. He laid out the whole grand vision in a 1996 book with a title that tells you everything about the man. He called it How Nature Works, not How Some Things Work, not a theory of certain systems. How nature works. Full stop, and he meant it. And this is where I have to be honest with you, in a way that the more breathless versions of this story never are. Because the honesty is what makes the rest of it trustworthy. Per Bak overreached. The claim that this one mechanism explains nearly everything was too big, and a lot of it did not hold up. And we are going to get to exactly where it broke. But the core of it, the part that survived every attack, is the part that matters for you. And it is this. There exist systems, real ones, not just computer toys, that slowly accumulate stress, that organize themselves to a critical state without anyone tuning them, and that then release that stress in avalanches whose sizes follow a power law with no characteristic scale and no predictable timing. A fault line is one of those systems. The stress builds over decades as the plates grind. The system sits at the critical edge, and it releases in earthquakes distributed exactly the way the sandpile predicted. Gutenberg and Richter found the pattern in 1944. Bak, 43 years later, found the reason. But notice what the reason costs you. If earthquakes are a self-organized critical system, then earthquake prediction in the sense people dreamed of, knowing that the big one is coming next Tuesday, is not merely difficult. It is forbidden by the structure of the thing. There is no precursor in the triggering grain, because the triggering grain is ordinary. The size of the avalanche is not determined until the avalanche is already running. You can know the distribution. You can know that over the next century a region will get roughly so many magnitude 6s and roughly so many 7s. You cannot know which slip becomes the catastrophe, because the slip itself does not know. I told you there was an experiment built to beat this, the most instrumented prediction effort in history, and that it failed. So now we can look at it, because now you can see why it was doomed before it began. But the pile of sand has one more secret to give up first, and it is the one that nearly killed the whole theory. And it involves a man pouring real grains down a real slope and watching the universe refuse to cooperate. The problem was that Bak's pile of sand lived inside a computer, and a computer grain of sand is a perfect, frictionless abstraction that does exactly what the rule says. Real sand is not like that. Real sand has weight and momentum and irregular shape. When a real avalanche gets going on a real pile, the moving grains build up speed, and that inertia carries the avalanche further than the simple toppling rule would predict, and it tends to produce avalanches of a similar large size over and over, rather than the clean power law spread of every size. Several groups tried it with actual sand in the early 1990s, and the results were a mess. The beautiful scale-free pattern that was so crisp in the simulation kept refusing to show up in the physical world. For a theory whose entire selling point was that it described real nature, this was close to fatal. The critics were not gentle, and some of them were right. The rescue came from Norway, and it is one of my favorite experiments in this entire story because of how humble the materials are. In 1996, a team based around the University of Oslo, with the lead author Vidar Fret, published a paper in the journal Nature with the gloriously unglamorous title Avalanche Dynamics in a Pile of Rice. They had built a thin pile, almost two-dimensional, sandwiched between two glass plates, and instead of sand they used rice, and they recorded avalanche after avalanche to see whether the size distribution followed a power law. And the answer was that it depended on the rice. This is the detail that I cannot stop thinking about. When they used long, thin, elongated grains of rice, the pile produced clean power law avalanches, scale-free, exactly as Bak's theory demanded. When they used rounder, more compact grains, it did not. The rounder grains produced avalanches with a characteristic size, a typical scale, the boring, ordinary kind of distribution, where extremes really are rare. The shape of the individual grain decided whether the entire pile lived in Bak's universe or in the ordinary one. Elongated grains catch and interlock and release their energy in a way that has no preferred scale. Round grains roll, and rolling has a natural size to it. The difference between a system where catastrophe has no upper limit and a system where it does turned out to hinge on whether the pieces were shaped like grains of rice or shaped like little beads. The authors were careful and honest about what this meant, and their conclusion is the single most important sentence for keeping this whole subject intellectually clean. Self-organized criticality, they wrote, is not as universal as was initially supposed. Whether a system shows it depends on the detailed mechanism by which the system dissipates its energy. In other words, Bak was wrong that it was everywhere. But he was right that it was real, and the rice proved it was real, because here was a physical pile made of a breakfast cereal that fell exactly onto the line. The phenomenon existed. It just was not the master key to the universe that Bak, in his less guarded moments, claimed it was. I want to dwell on this because it is the part that separates what we are doing here from the cheap version of this story. The version where someone tells you that everything is a power law and the universe is a sandpile and is not that profound. It is not that simple, and the not simple version is better. The truth is that some systems are poised at criticality and some are not, and the difference is in the physics of how they store and release stress. The systems that do show it share a family resemblance. They are driven slowly. They accumulate stress or energy over a long time. They release it suddenly through some threshold mechanism where one element failing pushes its neighbors past their own breaking point. A fault storing tectonic strain over decades. A forest accumulating dry timber over years. A financial system building up leverage and correlated bets over a boom, a power grid running closer and closer to its limits as demand grows. These are the systems where the catastrophe has no characteristic size, and these, you may have noticed, are not abstractions. They are the load-bearing structures of your life. So now, finally, the experiment. The place is called Parkfield, a tiny stretch of the San Andreas Fault in central California, and for most of the 20th century, it looked like the one place on Earth where earthquakes might actually be predictable. Parkfield had produced moderate earthquakes around magnitude 6, with what seemed like eerie regularity. There was one in 1857, one in 1881, one in 1901, one in 1934, and one in 1966. Lay those dates out and you see roughly 22 years between events, like a slow clock. In 1985, two seismologists named William Bakun and Alan Lind published the prediction, and the United States Geological Survey made it official, one of the only formal government-endorsed earthquake predictions ever issued. The next Parkfield earthquake, they said, would arrive before 1993, and they put a 95% confidence on it. They wired the place up like nothing before it. Strain meters, creep meters, seismometers, laser ranging, instruments to catch any whisper of a precursor, any change in the rock that might announce the coming quake. This was going to be the experiment that cracked prediction open. They were waiting for the difference, the signal in the fault that would say, now it is about to happen. 1993 came. No earthquake. 1994. 1995. The deadline passed and the fault sat there, instrumented to the teeth, doing nothing the instruments could read. As a warning, the Parkfield earthquake finally arrived on the 28th of September, 2004, 11 years late, and when it came, the most monitored patch of fault in the history of the planet produced essentially no usable precursor. The instruments recorded the earthquake beautifully. They did not see it coming. A later analysis by the seismologists David Jackson and Jan Kagan concluded, in the flat language these things get written in, that the prediction was unsuccessful and that its failure was exactly what you would expect from a simple null hypothesis, which is the polite scientific way of saying the fault was never going to tell anyone because the fault did not know. That is the abdication that should stay with you. It is not that the scientists were lazy or underfunded. They were neither. They spent decades and a fortune and pointed every instrument they had at the problem, and the problem turned out to be the wrong shape for a solution. You cannot predict the size or the timing of the next release in a self-organized critical system, not because you have not built a good enough instrument, but because the information you are looking for does not exist yet at the moment you want to read it. It comes into existence as the avalanche runs. The fault decides while it is breaking. The grain is ordinary until the pile is not. There is a place where that rule, the no characteristic size rule, killed close to 20,000 people in a single afternoon. And it killed them in large part because intelligent, careful, well-meaning people had convinced themselves that the rule did not apply to them. Off the northeast coast of Japan, along the trench where the Pacific plate grinds down underneath the country, seismologists had spent decades building a model of what that fault could do. The historical record and the prevailing theory told them the region produced earthquakes in the range of magnitude 7 to magnitude 8, large and dangerous, but bounded, and the possibility that this particular stretch of fault could generate a magnitude 9, the kind of rupture that tears along hundreds of kilometers of crust, was treated as essentially out of the question. There is even a name for the comfortable assumption underneath this, the characteristic earthquake idea, the belief that a given fault has a typical, natural size of event that it tends to produce. It is the bell curve smuggled into geology. It is the mild model chosen over the wild one, and the entire defensive infrastructure of that coast was built on it. The seawalls were sized for the expected event. The Fukushima Daiichi nuclear power station, sitting right on that coast, had its tsunami defenses designed against a wave whose height the characteristic model treated as the realistic worst case, a little under 6 meters. On the 11th of March, 2011, the fault did the thing the model said it could not do. It produced a magnitude 9.0 rupture, the largest earthquake in Japan's recorded history, releasing an amount of energy the characteristic assumption had ruled impossible for that place. The rupture drove a tsunami that in some locations reached heights of 14 and 15 meters, more than double what the defenses had been built to stop. The water came over the seawalls that had been sized for the comfortable world, and it killed somewhere around 18,000 people. The fault had not produced a special, unprecedented monster that came from nowhere. It had produced an ordinary earthquake from the same distribution as all the others, a single draw from the same straight line, far out on the tail where the official model had quietly decided, for the sake of comfort and planning and tractable engineering, to stop looking. And then came the cascade, because the catastrophe was not done with the wave. At Fukushima Daiichi, the earthquake severed the external power to the plant, and the tsunami, pouring over defenses built for a smaller world, flooded the backup diesel generators. And with both the primary and the backup power gone, the systems that circulated cooling water through the reactor cores stopped. Without cooling, the cores overheated, and 3 of them melted down, one failure loading the next. The lost grid power forcing reliance on the generators, the lost generators forcing reliance on batteries, the drained batteries leaving nothing at all. Each safeguard falling and shoving its burden onto the next exactly the way the transmission lines shove their load onto each other in Ohio, exactly the way the squares topple their neighbors in the pile. It became a nuclear disaster of the highest severity rating. Hundreds of thousands of people evacuated, an exclusion zone that persists to this day, the whole of it cascading out of one rupture that the planners had labeled impossible, because it sat too far out on a tail they had chosen to pretend was not there. The line had been there the entire time. They had simply preferred to believe it ended sooner than it does. And here is where the whole thing turns, where it stops being a story about geology and starts being a story about you. Because the moment you understand that the catastrophe has no characteristic size and the trigger is irrelevant and the timing is forbidden, you start seeing this pattern in places that have nothing to do with rock. The most disturbing place anyone ever found it was not in the ground. It was in us, in our wars. Somebody actually sat down and counted every war in modern history, sorted them by the number of dead, and asked whether human violence has a characteristic size. The man who did it was a pacifist. He was looking for a way to prevent war. And what he found instead was a law that says war behaves exactly like an earthquake, which is to say, it has no natural size at all. And the worst, one is always still out there on the line, waiting. His name was Louis Fry Richardson. He was born in 1881 into an English Quaker family, and he is one of those figures who turns up at the origin of 3 or 4 different fields and is properly remembered by none of them. He more or less invented numerical weather prediction, the idea that you could forecast the weather by dividing the atmosphere into a grid of cells and solving the physics equations cell by cell, which is exactly how every weather forecast on Earth is now produced, except that Richardson proposed it in 1922, decades before any machine existed that could do the arithmetic. He once estimated, only half joking, that it would take a workforce of 64,000 human calculators working in a vast hall to keep up with the weather as it happened. He was a generation early for the computer, and he knew it, and he did the work anyway. The Quaker part is not decoration. Richardson was a committed pacifist, and during the First World War, because he would not fight, he served as an ambulance driver on the Western Front, hauling the wounded and the dead out of the kind of carnage that does something permanent to a person. And there is a story about him that I find almost unbearable, because it shows you exactly the kind of man he was. He had been doing important early work on turbulence, the mathematics of how fluids and gases swirl and mix. At some point he realized that his turbulence research could be used to model how poison gas would disperse across a battlefield, how to deliver it more effectively onto human beings. And the account that comes down to us is that he stopped and that he destroyed or abandoned the work rather than let it serve that purpose. He walked away from his own science because of where it might lead. Hold that beside what he is about to discover, because the irony is going to get very heavy. After the war, Richardson wanted to understand the thing that had nearly broken him. He wanted to understand war itself, mathematically, the way he understood the weather, because he believed that if you could find the laws that governed it, you might find a way to prevent it. He spent years, decades on and off, compiling data on every violent conflict he could document, from the smallest to the largest, from individual murders up through riots and rebellions and colonial wars and the two world wars. He gathered it all into a single dataset, and the work was published after his death in 1960 under a title that is somehow both clinical and devastating. He called it Statistics of Deadly Quarrels. Now, the central problem Richardson faced was one of scale, and the way he solved it is the key to everything. How do you put a bar fight that kills one man and the Second World War on the same chart when one killed a single person and the other killed more than 60 million? The numbers are so far apart that no ordinary graph can hold them. Richardson's solution was to measure each conflict not by its raw death toll, but by the logarithm of its death toll, the number of zeros, essentially. A quarrel that killed about one person he called magnitude 0, 10 deaths, magnitude 1, 100, magnitude 2, 1,000, magnitude 3, and on up. By this scale, the world wars come out at around magnitude 7, meaning tens of millions. A single murder and a world war land on the same ruler, separated by 7 steps, the same way a tremor and a megaquake land on the seismologist's ruler. He chose that logarithmic scale for practical reasons because the data was imprecise and logarithms forgave the imprecision. But in choosing it, he did something he may not have fully intended. He built the exact same measuring stick that Gutenberg and Richter were building for earthquakes at almost exactly the same time, on the other side of the world, with no knowledge of each other. A seismologist measuring the violence of the earth and a pacifist measuring the violence of mankind reached for the identical mathematical tool. And when Richardson plotted his deadly quarrels by magnitude and asked how many big ones there were compared to small ones, he got the same answer Gutenberg and Richter got: a power law, a straight line. War has no characteristic size. Sit with what that means, because it is genuinely one of the bleakest sentences in the social sciences. There is no natural scale to human conflict. A skirmish that kills 12 people and a war that kills 50 million are not different kinds of event governed by different laws. They are the same phenomenon at different magnitudes, drawn from the same distribution, sitting on the same line. The thing that produces a border clash and the thing that produces a world war are not separable. And just as with the earthquake, the implication is that the conflict does not have its eventual size built into its beginning. Wars do not start as world wars. They start as ordinary quarrels, and most quarrels stay small, and a few cascade, and the math does not let you know in advance which is which. A duke is shot in Sarajevo, an utterly ordinary act of political violence of a kind that happened all the time, and the cascade does not stop, and 40 million people are dead within 4 years. The trigger was ordinary. The pile was not. And here is the irony I asked you to hold. Richardson, the pacifist, who walked away from his turbulence work because it might help kill people, spent the rest of his life trying to find the law of war so that war could be prevented. And what he found instead was a law that suggests it cannot be, not in the way he hoped. You cannot prevent the large war by being vigilant about its specific causes, any more than you can prevent the large earthquake by watching a single fault, because the large event is not caused by a special trigger. It is produced by the state of the system, by accumulated stress in the international order, the way strain accumulates in rock, and the specific assassination or border dispute that sets it off is just the grain that happened to land when the pile was full. He went looking for the off switch and found a thermostat that nobody controls. There is a strange and beautiful side road here that I have to take you down because it connects Richardson to the deepest mathematics of this whole subject. And it started, of all places, with a question about borders. Richardson, testing whether countries with longer shared borders went to war more often, needed to know the lengths of borders and coastlines. And he ran into something absurd. The published lengths of the same border disagreed wildly between sources. The border between Spain and Portugal was listed by one country as nearly 1,000 kilometers, and by the other as more than 1,200. How can a border have two different lengths? The answer Richardson uncovered is now called the coastline paradox. And it is this: the length of a coastline depends entirely on the length of the ruler you measure it with. Measure the coast of Britain with a ruler 100 kilometers long, laying it end to end, and you get one figure. Measure it with a ruler 50 kilometers long, and you can follow more of the bays and headlands, and you get a larger figure. Measure it with a ruler 1 kilometer long, and you follow every inlet and promontory, and the length grows again. Keep shrinking the ruler, measuring around every rock and every pebble, and the measured length does not settle down to a true value. It keeps growing, without limit, toward infinity. A coastline has no definite length. It has a length that depends on the scale at which you choose to look, and there is no correct scale. Richardson noticed this and published it almost as a curiosity, a footnote in a paper about war. And then, years later, a mathematician named Benoit Mandelbrot read that footnote, and it detonated. In 1967, Mandelbrot published a paper in the journal Science with the title, "How Long is the Coast of Britain?" And in it, he took Richardson's curiosity and turned it into a new geometry. The reason a coastline grows without limit, as you measure it more finely, Mandelbrot showed, is that it's self-similar. Zoom in on a piece of coastline, and it looks like a smaller coastline with the same kind of wiggles at every scale. A bay contains smaller bays, which contain smaller bays still. There is no scale at which the roughness smooths out into a simple line. Mandelbrot gave this property a number, a way of measuring how thoroughly a shape fills space. And a few years later, in 1975, he gave the whole idea a name. He called these shapes fractals, from the Latin for broken, and he spent the rest of his life showing that they are everywhere, in clouds and trees and lungs and lightning and rivers and mountains. And here is why that side road was worth taking, because the fractal and the power law are the same thing seen from two angles. A power law is what self-similarity looks like when you plot it as a distribution. No characteristic size in a distribution of events is the same statement as no characteristic scale in a shape. The coastline that has no true length, and the earthquake catalogue that has no typical magnitude, and the war record that has no natural size are all expressions of one underlying fact about certain kinds of systems. They are scale-free. They look the same at every magnification. And a scale-free system has a property that should be starting to feel ominous by now, because if there is no characteristic size, then there is no largest event that the system is somehow built to top out at. The distribution runs off toward the extreme with a probability that is small but never zero and never falls off a cliff. There is always a bigger one possible. The line does not end. I am going to make a turn now, and I am going to be explicit about it, because this is the hinge of the entire argument and I do not want you to miss it. Everything so far has been description. Earthquakes do this, wars do this, coastlines do this. Here is the math. Description is unsettling enough. But there is a second thing, an active thing, a thing we are doing right now, today, on purpose, to nearly every critical system we depend on. And the mathematics says it is the single most dangerous intervention available to us. We are suppressing the small events. We are stopping the little avalanches. And I need you to remember, when we get there, what a pile of sand does when you stop letting it have its small avalanches. Because the answer is that it does not become calm. It becomes a bomb. But before I can show you what we are doing to ourselves, I have to show you the one place where the stakes are measured in money instead of bodies, where this same scale-free monster was found hiding inside the most trusted equations in modern finance, and where the people who found it were ignored for almost exactly the reason you would expect. The truth was correct, and it was unprofitable to believe. Benoit Mandelbrot, the same man who turned Richardson's coastline into fractals, did not start with coastlines. He started with cotton. In the early 1960s, before the fractal work that made him famous, Mandelbrot got hold of a century of cotton price records, daily prices going back to the 1800s, and he did the thing he always did, which was to look at the data instead of looking at what everyone assumed the data should be. And in 1963, in a paper in the Journal of Business, he reported something that the entire edifice of modern finance was, even then, being built to ignore. To understand why it mattered, you have to understand what finance assumes. And the assumption is so deep that most people in the industry do not even experience it as an assumption. The foundational idea of quantitative finance is that the day-to-day wiggles of prices, the ups and downs, are distributed like the famous bell curve, the normal distribution, the same curve that describes human heights and measurement errors and the results of flipping a coin many times. The bell curve is the mathematics of the mild. In a bell curve, things are clustered tightly around the average, and the further you get from the average, the more vanishingly unlikely an event becomes. And it becomes unlikely extremely fast. Under the bell curve, an event 10 standard deviations from the mean, what the quants call a 10 sigma event, is so improbable that you would not expect to see one even once in many times the current age of the universe. The bell curve says the extreme essentially cannot happen. That is its central comfort, and it is the assumption underneath the pricing of options, underneath the measurement of risk, underneath the models that decide how much capital a bank must hold. Mandelbrot looked at the cotton prices and found that they did not obey the bell curve at all. The big moves, the violent jumps, were far too common. They came far more often and far larger than the bell curve permitted, and they did not taper off into impossibility the way the bell curve demanded. Instead, they followed a power law. The price changes had what statisticians call fat tails, or heavy tails, meaning that the extreme events, the crashes and the spikes, lived out at the end of the distribution with a probability that was small but emphatically not negligible, a probability that fell off slowly as a power law falls off rather than collapsing to nothing. Cotton prices, Mandelbrot showed, had no characteristic scale to their fluctuations, in exactly the sense that earthquakes have no characteristic magnitude and wars have no characteristic size. The same scale-free monster hiding in the price of a soft white commodity. He spent decades on this, and he laid it all out for a general audience late in his life in a book published in 2004, written with Richard Hudson, called The Misbehavior of Markets. And the numbers in that book are worth saying out loud, slowly, because each one is a small act of demolition against the comfortable model. Take the Dow Jones Index across the 20th century. Under the standard bell curve assumptions that finance actually used, a daily swing of more than 7% should be a once in 300,000 year event. It should, in other words, essentially never happen in a human lifetime, in a human civilization, in recorded history. The 20th century had 48 of them. Not one. 48. It gets worse, and the way it gets worse is precise. In the August of 1998, during the Russian financial crisis, the Dow fell in a particular three-step sequence. Mandelbrot calculated the odds of those three drops happening in that window under the standard model, and the answer was about 1 in 500 billion. He called it, dryly, the month the impossible happened. And the single most famous example, the one you may already half know, is Black Monday, the 19th of October, 1987. The day I opened this whole story with, when the market lost more than a fifth of its value in one session. Under the bell curve, that day was a 22 sigma event. Let me try to make 22 sigma mean something to you, because the number is so large it stops registering. A 10 sigma event already should not happen in the lifetime of the universe. 22 sigma is so far past that the probability is a decimal point followed by roughly 50 zeros before you reach a meaningful digit. It is a number so small that calling it astronomically unlikely insults astronomy. Under the model that priced the entire market, the 1987 crash could not occur. And then, on an ordinary Monday in October, it occurred. There is a currency example in the book that I find even more vivid because of the comparison he reaches for. A single day's move in an exchange rate, a drop of just under 8%, came out under the standard assumptions to a 10.7 sigma event, and Mandelbrot notes that an event of that rarity, under the bell curve, would not be expected to happen even once in the entire age of the universe, which is to say in roughly 14 billion years. It happened on a Tuesday. The kurtosis of daily stock returns, a technical measure of how fat the tails are, where the bell curve sits at a tidy value of 3, comes out for real markets at numbers like 43. The market is not a little bit wilder than the bell curve. It is wilder by a margin that makes the bell curve not an approximation, but a fantasy. There is a deeper piece of mathematics hiding underneath those numbers, and it is the thing that makes a power law different in kind from the bell curve rather than merely more extreme. And once you have seen it, you cannot plan the way you used to plan. Under the bell curve, the average is the center of everything. You take a sample, you compute the mean, and as you gather more data, the mean settles down to a stable, meaningful value, the typical case that everything clusters around. That is what an average is for. But for a power law with a heavy enough tail, and many of the real ones qualify, the average does not behave. The variance, the standard measure of how spread out the data is, can be mathematically infinite, which means it never settles no matter how much data you collect. And for the most extreme power laws, even the mean itself fails to converge, because every so often a single event arrives so much larger than everything before it that it dominates the entire average on its own and hauls it to a new value, and then a larger one comes and hauls it again. Think about what that does to the very idea of a typical case. Line up 1,000 people and measure their heights, and the average is meaningful, because no person is 1,000 times taller than another. The tail is bounded. The average is a number you can build a doorway around. Now line up the same 1,000 people and measure their wealth, and the average becomes close to a lie, because the moment one billionaire walks into the room, the average net worth leaps to a figure that describes nobody present. Not the billionaire, and certainly not the other 999. The average wealth is not the wealth of a typical person. It is an artifact of the single largest person in the sample, and it will jump again the instant someone richer arrives. Wealth is a power law, which is exactly why the average is meaningless and only the median tells you anything true. Earthquake energy is like wealth, not like height. War deaths are like wealth, not like height. Market losses are like wealth, not like height. In every one of these systems, the largest single event can carry more weight than the entire rest of the record combined, which means there is no stable average to plan around, no typical year, no characteristic disaster you can prepare for and then call yourself ready. The single largest earthquake, the single worst crash, the single deadliest war can each outweigh the sum of everything smaller that ever came before them. And the mathematics does not merely permit this, it guarantees that across a long enough span, it happens. So when you build your defenses around the average event, or even around the worst event in living memory, you are not being prudent. You are measuring the height of a room that wealth is about to walk into. Remember Japan. The defenses were sized for the typical event, and the typical event is not the one that kills you. And here is the part where the controlled intensity I have been trying to maintain gets harder to maintain, because this is not a story of an honest mistake. The fat tails were known. Mandelbrot published them in 1963. The evidence accumulated for decades, and the field built its models on the bell curve anyway, and went on building them, and is still building them. And the reason is not that the power law was disproven. The reason is that the bell curve is mathematically convenient and emotionally comfortable and lucratively tractable. You can price an option cleanly under the bell curve. You can compute a tidy risk number, a single figure called value at risk, that tells a bank exactly how much it can lose on a bad day. And that number lets you take on more leverage and book more profit. And it is built on the assumption that the truly bad day, the tail, essentially does not exist. The power law offers no such comfort. Under a power law, there is no clean worst case, no number you can put in the box, because the tail runs off toward the extreme, and the next event can always be larger than anything in your records. Finance had a choice between a model that was tractable and a model that was true, and it chose tractable, and it has chosen tractable over and over every time the question has come up. The most expensive demonstration came in 1998. A hedge fund called Long-Term Capital Management had been built by, among others, two economists who had won the Nobel Prize for the very auctions pricing mathematics that rests on the bell curve assumption, Myron Scholes and Robert Merton. The fund was a temple to the idea that risk could be precisely measured and managed using these models. It was leveraged to an extraordinary degree on the confidence that extreme events were as rare as the bell curve said. And in the late summer of 1998, the markets moved in a way the models said should not happen. The tail arrived on schedule the way tails do, and the fund lost most of its capital in a matter of weeks and had to be rescued in an emergency operation coordinated by the Federal Reserve to keep it from taking the financial system down with it. The men who had won the highest honor in economics for the mathematics of risk were destroyed by a risk their mathematics had defined as impossible. And then it happened again, larger, in 2008, when the same assumption, dressed in newer clothes, helped engineer a collapse that cost the world economy trillions, and that an enormous apparatus of professional risk managers using bell curve tools did not see coming because their tools were built to not see it. This is the abdication of authority in its purest financial form, and it is worth naming exactly what it is, because it is not a conspiracy and it is not stupidity. It is a profession that found the truth inconvenient and chose structurally, institutionally, to keep using the falsehood because the falsehood paid better and felt safer right up until the moment it did not. Mandelbrot said as much, plainly, for 40 years, and the field treated him as a brilliant eccentric whose mathematics was too pessimistic to be practical. Which is a remarkable phrase when you think about it. The idea that a description of reality can be too pessimistic to use, as if reality were obligated to be as mild as the model that is convenient for us. But Mandelbrot, for all that he was right about the fat tails, made a kind of peace with the unpredictability. His position, in the end, was close to Per Bak's. The big crashes are part of the distribution. They are wild, but they are normal for a wild system. And you cannot predict any individual one. You can only respect the fat tail and stop pretending it is thin. That was the heresy, and it was a deep one. And then a physicist named Didier Sornet stood up and committed a heresy against the heresy. He looked at the same crashes and said that some of them, the very largest, are not part of the distribution at all. They are a different animal. And he claimed, against Bak, against Mandelbrot, against the whole grain of everything I have told you so far, that some of these catastrophes can be seen coming, that the system, before the largest collapses, sends up a signal, and the fight between those two positions, the unpredictable pile against the predictable dragon, is not settled. And it is the most important open question in this entire field. And it is where we have to go next. Didier Sornet is a French physicist born in 1957 who came into finance the way a few dangerous people do, from the outside, carrying tools built for something else. His background was in the physics of materials that fail, the study of how a solid object under stress develops tiny cracks that grow and link up until the whole thing ruptures. He had also worked on earthquakes and on the rupture of pressure tanks, and he spent years at the University of California before settling at the Swiss Federal Institute of Technology in Zurich, the institution usually called ETH Zurich, where he eventually held a chair with the almost theatrical title of Professor of Entrepreneurial Risks. And what Sornet claimed, and has claimed for more than 20 years, is that a financial bubble is not a vague metaphor about exuberance. It is a physical system approaching a rupture, and ruptures, he insists, are not always silent before they come. His argument, laid out in his 2003 book Why Stock Markets Crash, goes like this. In a bubble, investors do not act independently. They watch each other. They imitate. When a market is rising and everyone around you is making money, the pressure to join, to copy, to follow the herd grows, and that imitation creates feedback. And the feedback drives the price up faster and faster. Sornet modeled this with the same mathematics physicists use for a system approaching a critical point, where local elements, spins in a magnet, atoms in a freezing liquid, suddenly begin to align with their neighbors over longer and longer ranges. As a bubble approaches its critical moment, he argued, the imitation becomes so widespread that the price accelerates not just steadily, but super exponentially, racing toward what the mathematics calls a finite time singularity, a point at which the trend would, if nothing stopped it, become literally infinite. It cannot reach infinity, of course. Something always breaks first. The crash is the break. And here is the signature that, if Sornet is right, separates his view from Bak's. As the bubble approaches that critical point, the price does not just accelerate smoothly. It oscillates, and the oscillations get faster and faster, compressing as they approach the critical time, like a bouncing ball, settling like the accelerating wobble of a spinning coin just before it falls flat. He calls this pattern a log periodic power law signature, and his claim is that you can sometimes see it forming in the data of a real bubble before the crash, and that from it, you can estimate, not perfectly, but probabilistically, the window in which the system is most likely to rupture. In 2008, as the financial crisis broke, and economists everywhere were declaring that no one could possibly have foreseen it, Sonnet founded an institute at ETH Zurich called the Financial Crisis Observatory, with the explicit purpose of diagnosing bubbles in real time, watching the world's markets for the accelerating, oscillating fingerprint of a system heading for the edge. Now, if you have been paying attention, you should feel a contradiction, because everything I told you for the first half of this story said that the timing of the big avalanche is forbidden, that the trigger is irrelevant, that the system gives no warning. And Sonnet is saying, in at least some cases, that is wrong. There is a warning. The system does announce itself. Both of these cannot be fully true. And the place where Sonnet draws the line is an idea he introduced in a 2009 paper, and it is one of the most provocative ideas in the whole subject. He calls them dragon kings. Remember that on a clean power law, the events are all drawn from the same distribution. The big ones are just the rare draws from the same line as the small ones, which is exactly why they are unpredictable. Because they are not special, they are just large. Sonnet's claim is that some real systems produce events that are too large even for the power law, events that sit above the line, that are statistical outliers, even in a distribution that is supposed to have no outliers, that are so big they betray the presence of a different mechanism, an extra layer of feedback that kicks in only in the largest events and amplifies them beyond what the ordinary distribution would ever produce. He named them dragon kings to capture both that they are enormous kings and that they are a genuinely different kind of beast. Dragons, not just big lizards. And his argument is that because a dragon king is produced by a specific identifiable mechanism, rather than by the blind statistics of the tale, it is precisely the kind of catastrophe that might be predictable and even preventable if you can detect the mechanism switching on. This put him in direct opposition not only to Bak, but to another famous figure you have probably heard of, Nassim Taleb, whose Black Swan is almost the mirror image of the Dragon King. Taleb's whole point is that the world-breaking events are fundamentally unpredictable, that they come from outside the model, that the search for warning signs is a fool's errand, and the only sane response is to build systems that can survive shocks you cannot foresee. Sonnet looked at that and said, in effect, some of your black swans are not black swans at all. They are dragon kings. They have a mechanism, and the mechanism leaves tracks. The disagreement is not academic, not come. Was the model wrong, or was the risk real, and the system simply got lucky? The Dragon King idea is taken seriously by serious people, and it is also genuinely contested. And the honest position is that we do not yet know how often the largest catastrophes announce themselves, and how often they arrive in total silence. But here is the thing that I keep coming back to. The thing that makes the Bak versus Sonnet fight matter to you, even though it is unresolved. And it is a move I want you to watch carefully because it is the consensus underneath the disagreement. Bak says the big one comes without warning. Sonnet says the big one sometimes sends a signal. They are arguing about the warning. They are not arguing about the big one. Both of them, the pessimist of pure randomness and the optimist of the detectable mechanism, agree completely that the large catastrophe is coming, that it is built into the structure of these systems, that it is not an aberration to be engineered away, but a feature to be expected. The entire furious disagreement between the two camps is about whether you get a few weeks of advance notice. Neither side, not one researcher in this field, is telling you the big one might not come? That question was settled by the straight line, and the straight line does not bend. Which would be a clean place to land, except that I have been quietly assuming something this entire time, that a group of statisticians decided to attack head-on, and their attack is the most serious challenge to everything I have told you. And if I skip it, I am doing exactly what I accuse the finance industry of doing, which is choosing the comfortable version. So, before we go to the part where we make all of this worse with our own hands, I have to tell you about the people who looked at the straight line and asked the most dangerous question available. What if a lot of these are not power laws at all? For about 2 decades after Bak, there was a kind of gold rush. Self-organized criticality and power laws became fashionable, and researchers went looking for the straight line everywhere, and they kept finding it. In the sizes of cities, the number of links to web pages, the frequency of words, the sizes of wars, the magnitudes of solar flares, the populations of species, the citations of scientific papers. Paper after paper announced a new power law in a new system, and the way almost all of them announced it was the same. They took their data, they plotted it on a graph, with logarithmic axes on both sides. They looked at the result, they saw something that resembled a straight line, and they declared a power law. It became almost a reflex. See a straightish line on a log-log plot. Write the word power law. Publish. In 2009, 3 researchers decided this had gone far enough. Aaron Clauset, Cosmara Hiller-Shalizi, and Mark Newman, working between the Santa Fe Institute and several universities, published a paper in the journal SAM Review with a deceptively dry title, Power Law Distributions in Empirical Data. And it was, in effect, a demolition of the methods most of the field had been using. Their central technical point was that fitting a straight line to a log-log plot is a genuinely terrible way to identify a power law, because it is biased and unreliable in ways that systematically fool the human eye. The physicist Peter Grasberger put the problem with beautiful bluntness. Log-log plots, he noted, have a notorious tendency to suggest linear curves even when there are no real power laws there at all. Your eye wants to see the line. The plot is built to flatter that wish. A whole range of distributions that are not power laws will, on a log-log plot, look convincingly straight over the limited range of any real dataset. So Clauset and his colleagues built a proper statistical machine to test the claims honestly. Instead of eyeballing a plot, they used a rigorous fitting method called maximum likelihood, then ran a formal goodness of fit test to ask whether a power law was even a plausible description of the data. And then, crucially, they pitted the power law against its rivals, distributions like the log normal and the stretched exponential, which are also heavy-tailed, which also produce lots of large events, but which are not scale-free, which do eventually have a characteristic scale, hiding far out in the tail. And then they took the most famous claimed power laws in the literature, 24 of them, the celebrated examples that got cited again and again, and they ran them through the machine. The results were humbling. For many of the famous data sets, the power law could not be cleanly distinguished from a log normal. For some, the log normal or the stretched exponential actually fit better. A good number of the confident published power laws turned out to be, under rigorous testing, merely consistent with a power law, no better supported than several alternatives that tell a different story about the underlying mechanism. The straight line that launched 1,000 papers was, in a depressing fraction of cases, an artifact of a lazy method and a hopeful eye. I want to be very careful here, because this is the moment where it would be easy to overcorrect into the opposite error and tell you that the whole thing is debunked, that power laws are a myth, that the sandpile was a delusion. And that is just as wrong as the gold rush was. The closet paper did not destroy the field. It disciplined it. And here is what survived the discipline, because what survived is the part that should still keep you up. Earthquakes survived. The Gutenberg Richter law is one of the most robustly confirmed power laws in all of science, tested against enormous catalogues, and it does not flinch under the rigorous methods. Solar flares survived strong testing. The largest wars, Richardson's deadly quarrels, hold up as a power law above a certain size with real statistical support. The systems I told you to care about, the ones that slowly accumulate stress and release it through cascading thresholds, the faults and the fires and the grids and the leveraged markets, are exactly the systems where the heavy tail is most solidly established. The places where the power law claims fell apart were often the softer ones, the social and biological data sets where the mechanism was always more of a story than a measurement. And even where the strict power law fails, look at what it fails into. It does not fail into the bell curve. Nobody ran the rigorous tests and discovered that earthquakes or market crashes or blackouts are actually mild, that the extremes are vanishingly rare after all, that we can all relax. When a claimed power law loses to a log normal or a stretched exponential, the winning distribution is still heavy-tailed. It still produces catastrophes vastly more often than the bell curve allows. The argument between the power law and the log normal is an argument between two different shapes of monster, an argument about whether the tail is infinitely scale-free or merely enormous, about whether there is a faint characteristic scale lurking 10 magnitudes out. It is not an argument about whether the monster exists. The monster is not in dispute. Whether you describe these systems with the purest version of Bak's mathematics or with a more cautious, heavy-tailed cousin, the operational truth is identical. Large catastrophes are far more probable than our intuitions and our comfortable models assume. The next one can be larger than anything in the record, and the timing is not written anywhere you can read it. That is the intellectually honest version, and it is more disturbing than the hype version, not less, because you cannot escape it through the usual exit. The usual exit, when someone tells you something frightening about the world, is to find the methodological flaw, the overstatement, the place where they pushed too hard, and to use that flaw to dismiss the whole thing and go back to sleep. Per Bak gave you that exit because Per Bak overstated his case, and the Rice and the statisticians found the seams in it. But when you take the exit, when you strip away everything Bak overclaimed, when you keep only what survives the harshest available criticism, you are left standing in the same place. The systems you depend on are heavy-tailed. The big one is coming. You will not be told when. The exit leads back into the room. So we have run out of ways for the math to save us. The catastrophe is built in. The timing is hidden. The critics could not make it go away. And this is the moment where the story stops being about understanding a frightening fact and starts being about what we have chosen to do in the face of it. Because here is the thing we have done. Faced with systems that produce catastrophes of every size, we have spent the last century becoming extraordinarily good at stopping the small ones. We put out the small fires. We bail out the small failures. We smooth over the small corrections. It feels like wisdom. It feels like exactly what a responsible civilization should do. And it is, the mathematics says, very close to the worst possible thing you can do to a system like this. And to understand why, we have to go to a forest in Wyoming in the summer of 1988, where 100 years of putting out small fires came due all at once. For most of the 20th century, American policy toward forest fire was simple and intuitive, and catastrophically wrong. Fire was the enemy. After a devastating fire season in 1910 that killed dozens of people and burned millions of acres, the young United States Forest Service committed itself to total suppression. And by 1935, that commitment had hardened into something called the 10 in the morning rule, a directive that every fire should be brought under control by 10 o'clock the morning after it was first reported. Every fire, the little ones, the natural ones, the ones started by lightning that had been part of these ecosystems for millions of years before there was anyone to put them out. Smokey Bear told a couple of generations of children that only they could prevent forest fires, and the children grew up believing that a forest without fire was a forest being protected. But a forest is one of those slowly driven, stress-accumulating, threshold-releasing systems, and the stress it accumulates is fuel, dead wood, fallen needles, dense undergrowth, young trees crowding in where a fire would normally have thinned them. In a forest left to itself, small fires burn through every so often, clearing out the accumulated fuel, killing the undergrowth, leaving the big fire-resistant trees standing and resetting the system. The small fires are the small avalanches. They are how the pile sheds its stress a little at a time. And what total suppression does, what the 10 in the morning rule did across tens of millions of acres for the better part of a century, is stop the small avalanches. Every small fire put out is fuel that did not burn, fuel that stays on the forest floor and accumulates year after year, decade after decade, while the forest grows quietly more and more loaded, climbing toward a critical state that no one is watching because the absence of fire looks exactly like safety. There is a model of this, clean and brutal, called the forest fire model, developed by the physicists Barbara Drossel and Franz Schwabel in 1992, and it is essentially Bark's sandpile wearing bark. Trees grow at random on a grid, slowly. Lightning strikes at random, rarely. When lightning hits a tree, fire spreads to every tree connected to it, and the size of the resulting fire depends entirely on how densely the forest has grown, on how connected the trees have become. Run the model and the fire sizes follow a power law. No characteristic size, most fires small, a few enormous, scale-free, and the model shows you the thing the policymakers could not see. The more you suppress the small fires, the denser the forest grows, the more connected it becomes, and the larger the eventual unavoidable fire will be when it finally comes. Because by then, the entire forest is one connected mass of fuel, and a single ignition can take all of it. You do not remove the fire by suppressing it. You defer it, and you make it bigger, and you concentrate a century of avoided small catastrophes into one large one. In the summer of 1988, the bill came due in Yellowstone. It was the driest year in the park's recorded history, and the forests of Yellowstone had been accumulating fuel under suppression policy for decades. Fires started in June, as they always did, from lightning, and under the old reflex, they were small and would have been fought immediately. But policy had begun to shift toward letting natural fires burn, and these were allowed to run. And then the drought deepened and the winds came, and it was far, far too late for the forest to shed its load gently. The fires grew and merged and became something the firefighters could only flee from. On a single day, the 20th of August 1988, a day that came to be called Black Saturday, high winds drove the flames across more than 150,000 acres in hours. By the time the snows of autumn finally put it out, the fires had burned close to 800,000 acres inside the park, more than a third of Yellowstone itself, with something like 1.4 million acres burned across the greater Yellowstone region. More than 25,000 firefighters cycled through. The effort cost around $120 million, and almost none of it mattered, because you cannot fight a fire on that scale. You can only get out of its way and wait for the weather to change. The forest released a century of suppressed stress in a single season, and there was nothing any number of firefighters could do, because the catastrophe had been built quietly, fuel load by fuel load. Every time someone responsibly put out a small fire that nature had sent to do the work the big fire was now doing all at once. This pattern, the way that making a system safer against small failures makes it more vulnerable to a catastrophic large one, is general, and it has a name, and the name comes from two researchers who turned it into rigorous theory. In 1999, the physicist Jean Carlson and the control engineer John Doyle published a framework they called highly optimized tolerance, and it is the dark twin of Bak's idea. Bak said systems organize themselves to criticality on their own, blindly, with no designer. Carlson and Doyle said something more pointed and, for us, more damning. They said that when you take a system and optimize it deliberately, intelligently, to be robust against the failures you expect and the disturbances you see most often, you tend to make it exquisitely fragile against the rare failures you did not design for. They had a phrase for the result, and once you have heard it, you will see it everywhere. Robust, yet fragile. A system tuned to handle its common stresses beautifully and precisely because it is so tuned, primed to fail spectacularly and totally when something hits it that the optimization did not anticipate. The forest under suppression is robust, yet fragile. It handles the routine perfectly. No annoying small fires. Decades of green, untouched wilderness. And it is being loaded the entire time toward a single fire that takes everything. And the reason this should frighten you more than the pure sandpile is that the sandpile finds its critical state blindly on its own, but we walk our own systems toward criticality on purpose, with the best intentions, congratulating ourselves on our prudence the whole way. Every small fire we put out, every small failure we prevent, every small correction we smooth over feels like competence, feels like exactly what a careful steward should do. And each one quietly adds to the fuel. We are not failing to manage these systems. We are managing them intensely. And the management is loading the tail. And nowhere is that clearer. Nowhere is the robust yet fragile trap more total than in the two systems that the entire modern world is balanced on top of. The grid that carries the electricity and the financial system that carries the money. Both of them have been optimized for efficiency and robustness against small failures for decades. Both of them, the people who study them most closely will tell you, are sitting exactly where the forest was in the summer of 1988. Go back to the 14th of August, 2003, and look at how the lights actually went out, because the anatomy of that day is the sandpile made of copper and high voltage. It began in Ohio on a hot afternoon with something almost insultingly small, a few high-voltage transmission lines carrying more current than usual on a hot day when air conditioners were straining, sagged as they heated the way loaded wires do, and sagged into trees that had not been trimmed back far enough beneath them. The contact with the trees tripped the lines out of service. That is it. That is the grain of sand. Untrimmed trees and a hot afternoon, a problem so ordinary it happens somewhere in the grid, constantly. What turned that ordinary problem into a catastrophe was the connectedness and a piece of terrible luck that is itself part of the pattern. The control room software that was supposed to alert the operators to the problem had a flaw, and the alarm system silently failed, so the people whose job it was to manage the grid did not know for over an hour that anything was wrong. And while they sat blind, the physics did what physics does in a connected network at its limits. When those first lines dropped out, the power they had been carrying did not vanish. It had to go somewhere, so it redistributed onto neighboring lines, which were now carrying more than before, which pushed some of them past their own limits, which tripped them out, which shoved their load onto the next lines, which tripped. One section failing loaded the next section past its breaking point, which failed and loaded the next. This is precisely, mechanically, the toppling rule of the sandpile, except the grains are megawatts, and the toppling is a circuit breaker opening. The cascade accelerated, raced across the northeast faster than any human could respond, and in the space of about an hour it had switched off the electricity for around 50 million people across 8 American states and the Canadian province of Ontario. It contributed to at least 11 deaths and cost something on the order of $6 to $10 billion. From sagging lines in Ohio to 50 million people in the dark, in an hour, through a chain of individually small failures that each pushed the next element over its threshold. This is not an accident waiting to be engineered away, and the researchers who study it most carefully say so, in language that is genuinely alarming once you understand what they mean. A group including Ian Dobson, Benjamin Carreras, David Newman, and others spent years analyzing the statistics of power grid blackouts, and what they found is that blackout sizes, measured by how many customers lose power or how much load is lost, follow a power law. No characteristic size, most blackouts small, a few enormous, the same scale-free signature as earthquakes and fires and wars. And they argued that this is because the grid, like the forest and the fault, is a self-organized critical system. It is driven slowly by ever-growing demand for power. It is held back from failure by engineers who upgrade and reinforce it in response to problems. And the balance between the growing load and the engineering response naturally pushes the grid toward its critical point and holds it there, perpetually poised the way the sandpile poises itself, so that an ordinary triggering event can produce an avalanche of any size up to and including the collapse of an entire interconnected region. And then they said the thing that should be printed on the wall of every control room in the world. When the work of Carreras and Dobson and their colleagues was described in the wider press, the summary was blunt. Power grids are inherently prone to large blackouts, and efforts to make them more robust can make the problem worse. Read that again with the forest in your mind. The grid is robust yet fragile. Every time we reinforce it against the small, common failures, every time we add the protective relays and the automatic responses that prevent the minor outages, we make the system more tightly coupled, more optimized, more efficient, and we push the critical point higher so that when the truly large cascade does come, it is larger than it would have been, sweeping through a system we made more connected in the name of making it more reliable. The Northeast blackout of 1965, generations earlier, took out around 30 million people through the same kind of cascade. We studied it, we reinforced the grid, we made it more robust, and in 2003, the cascade took 50 million. We are not getting better at preventing the big one. We are getting better at preventing the small ones, which is not the same thing, which is in fact the opposite thing. And the grid does not only have to survive its own internal cascades, it sits exposed beneath the single most powerful critical system anywhere near us, which is the sun. And the sun has avalanches of its own. The surface of the sun is a churning tangle of magnetic field, endlessly twisted and stressed by the plasma moving beneath it, storing energy the way a fault stores strain, and it sheds that energy in solar flares, sudden eruptions of radiation, and in larger events called coronal mass ejections that hurl billions of tons of charged particles out into space. In 1991, two physicists named Edward Lu and Russell Hamilton published a paper in the Astrophysical Journal arguing that the sun's outer atmosphere is a self-organized critical system. The sandpile again, 93 million miles away and made of plasma instead of grain. They showed that the energies of solar flares follow a power law across many orders of magnitude, most of them small, a rare few enormous no characteristic size. And they described a single flare as an avalanche made of many small magnetic events, cascading into one another, language they could have copied straight out of Per Bak. The sun releases its accumulated stress in exactly the scale-free, no upper limit, unpredictably timed avalanches you have now seen in the ground and the markets and the forests. Most of those solar avalanches miss us or wash harmlessly over the planet's magnetic field, but not all of them. And there is one event in the record that shows you what the tail of the solar distribution is capable of. On the 1st and 2nd of September, 1859, a British astronomer named Richard Carrington was sketching sunspots when he watched a patch of the sun suddenly blaze white, the first solar flare ever witnessed by a human being. About a day later, the storm reached Earth, and what followed is the reason the event still carries his name. Auroras, the northern lights, were seen so far from the poles that people in the Caribbean and near the equator woke to glowing skies, and the telegraph network, the only electrical infrastructure that existed anywhere on Earth in 1859, convulsed. Telegraph lines threw sparks. Operators received electric shocks from their own equipment. Some telegraph offices caught fire. In a handful of places, operators disconnected their batteries entirely and discovered they could keep sending messages on nothing but the current the storm itself was driving through the wires. Now take the Carrington event, a draw from the far tail of the solar power law, and set it down on top of the grid we just spent so long describing. The vast, continent-spanning, tightly coupled, robust yet fragile lattice of high-voltage lines and transformers that the entire modern world runs on, none of which existed in 1859. A large geomagnetic storm induces electric currents in long conductors, and the longer and more interconnected the conductors are, the more they catch, which means the enormous, expensive, slow-to-replace transformers at the heart of the modern grid are precisely the components most exposed. Researchers who study this have warned that a Carrington-class storm striking the grid as it exists now could destroy transformers across whole continents at once and produce blackouts lasting not hours, the way 2003 lasted hours, but months, because there is no warehouse full of spare transformers and each one takes a long time to build. And we have come close. In 1989, a far smaller storm collapsed the power grid of the entire Canadian province of Quebec in about 90 seconds, leaving millions in the dark. In 2012, a coronal mass ejection on the scale of the Carrington event erupted from the sun and tore straight across Earth's orbit. And the only reason it did not hit us is that the Earth had not yet arrived at that point in its path around the sun. It missed by roughly a week. It is the same story one more time, scaled all the way up to a star. A critical system shedding stress in avalanches of every size. A tail with no ceiling, a timing that nobody can hand you. And waiting underneath it, the same fragile, optimized, over-connected human machinery, ready for the grain, whether the grain falls from a tree in Ohio or from 93 million miles away. Now hold the grid in one hand and pick up the financial system in the other, because they are the same shape and we treat them the same way. After every market crisis of the last several decades, the response of the authorities has been, broadly, to step in and stop the cascade, to backstop the failing institutions, to inject liquidity, to cut interest rates, to do whatever it takes, in the famous phrase, to keep a local failure from spreading. And in the immediate moment, this is almost always the right call, because the cascade in front of you is real, and the human cost of letting it run is real. But step back and look at what the policy does across decades, because across decades, it is fire suppression. Every small correction smoothed over, every minor crisis backstopped, every failing institution caught before it can fail, teaches every participant in the system that the small avalanche will not be allowed to happen. And so they take on more leverage, more risk, more tightly correlated bets, building the financial equivalent of fuel load, growing the connections between institutions denser and denser, until the system is so interconnected that there are no small fires left to burn, only the one large one that has been deferred and is therefore, when it finally comes, the only size left available to it. 2008 was that fire, partially. The system was so connected that the failure of pieces of it threatened all of it, which is exactly why it had to be backstopped, which taught everyone the lesson again, which is why the connections have only grown since. We have built, deliberately, in the name of safety and efficiency, two of the most highly optimized, tightly coupled, robust yet fragile systems in human history, and we have wired them into each other and into everything else. And the most disturbing scope of this is not the grid or the markets individually. It is that the entire structure of modern civilization has been moving in one direction for 2 centuries, the direction of more connection, more optimization, more efficiency, more removal of the slack and the redundancy and the small local failures that used to keep catastrophes contained. Every supply chain stretched tighter and more global, every system more dependent on every other system. We have been taking a planet full of loosely coupled local piles, each of which could only ever have a local avalanche, and welding them into one enormous, exquisitely optimized, globally connected pile. And we have been congratulating ourselves on the efficiency the entire time. The mathematics has a quiet prediction about what happens to the size of the largest possible avalanche when you do that. And you already know what the prediction is, because you have understood the sandpile since the beginning of this. There is no longer an upper limit you can point to. The line just runs off the edge of the page. There is one more pile, the largest and slowest of all, and it is the one that made you. Life on Earth is also a slowly driven system that accumulates something, in this case, ecological complexity, species woven into food webs, each one depending on others, the whole biosphere growing more interconnected over millions of years. And it also releases that accumulated tension in sudden collapses, and we call those collapses mass extinctions. In the early 1980s, 2 paleontologists, David Raup and Jack Sepkoski, did for the fossil record what Gutenberg and Richter did for earthquakes, and Richardson did for war. They compiled the marine fossil record into a vast database, and they looked at the pattern of extinction through deep time, and they found that extinction is not a smooth background process. It comes in bursts, long stretches of relative stability punctuated by sudden collapses of wildly varying size, from minor pulses up to the great dyings, the same uneven, bursty, no characteristic scale signature you have now seen in every other system in this story. Whether the sizes of extinctions follow a strict power law is one of the genuinely contested questions, and I am not going to pretend it is settled, because it is not. Raup and Sepkoski went further and claimed the great extinctions came on a roughly 26 million year cycle, and that claim has been argued over for 40 years without resolution. But Per Bak, characteristically, could not resist. In 1993, he and a collaborator named Kim Sneppen built a model almost insultingly simple of species co-evolving, each one sitting at some level of fitness, the least fit one always being the one to go extinct or mutate, which then disturbs the species connected to it in the food web, which can trigger a cascade of further extinctions. And the model self-organizes to criticality and produces extinction events, with a power law distribution of sizes and the same 1/f signature in time. It was Bak's way of saying that the long stillnesses and sudden collapses that paleontologists like Stephen Jay Gould and Niles Eldredge had named punctuated equilibrium were not a special biological mystery. They were criticality, the sandpile again, evolution poised on the same knife edge as everything else. Most changes small, a few of them clearing most of the life off the planet. And the largest of those clearings is the reason you are reading this. Around 66 million years ago, an asteroid struck what is now the Yucatan, and in the cascade that followed, something close to 3/4 of all species on Earth went extinct, including every dinosaur that was not a bird. That was, by any measure, a catastrophe so far out on the tail that it is hard to hold in the mind. And it was also the single most important event in your personal ancestry, because the dinosaurs had spent over 100 million years occupying every large ecological niche on the planet and keeping the small, scurrying mammals pinned to the margins. And when the catastrophe cleared them away, it was the mammals who inherited the emptied world. And it is from those survivors, those small things that lived through the worst day in the history of complex life, that you are descended. The asteroid did not interrupt the story of your existence. It started it. You are not standing apart from the catastrophes, looking at them as someone else's disasters in someone else's systems. You are a product of the largest avalanche the biosphere ever had. The catastrophe is not the exception to life. It is the editor of it. And there is one last place this pattern appears, the most intimate place there is, which is inside the organ you are using to follow this sentence. For a long time, the assumption in neuroscience was that the brain, in order to work reliably, must hold itself well clear of anything like a critical instability, because criticality sounds like runaway chaos, and runaway chaos in the brain sounds like a seizure. In 2003, two researchers named John Beggs and Dietmar Plenz placed thin slices of cortical tissue onto grids of electrodes and watched the spontaneous ripples of firing that move through neural tissue on their own. The bursts were not all the same size, and they were not clustered around a typical size. They arrived as cascades, one cluster of neurons firing and tipping the next into firing, and the sizes of those cascades followed a power law. Beggs and Plenz named them neuronal avalanches, and the slope of the power law they measured came out remarkably close to the value from Bak's sandpile, the same 1.5 that falls out of grains, toppling on an idealized grid. A sliver of brain on a dish was organizing itself to criticality, the same knife edge, the same scale-free avalanches as the fault and the forest and the sun. This has grown into one of the most provocative ideas in living neuroscience, the critical brain hypothesis. And the claim is roughly this: the brain does not flee the critical point. It seeks it out and balances on it, because a system poised at criticality has exactly the properties a thing needs if its job is to process information. At the critical point, a network is maximally sensitive, so a faint input can propagate across the whole of it, and it holds the largest possible range of distinct patterns, and signals travel across it with the least loss. On this view, the brain is tuned to the same edge as the sandpile, not in spite of the danger, but because the edge of the cascade is precisely where a network becomes rich enough to compute, to perceive, to think. It is contested, like everything honest in this field, and some argue the signatures can appear without true criticality underneath, the same caution the statisticians taught us. But the core finding, scale-free avalanches running through living neural tissue, has been reproduced many times, and the thought you are having right at this moment, the one weighing whether to believe any of this, may itself be one of them, a cascade of firing crossing your cortex, drawn from a power law with no characteristic size. And that closes a loop I opened near the beginning without telling you it was a loop. I said that 1 over F noise the flicker Bak's whole theory was built to explain turns up in the rhythm of your own heartbeat. It does. The intervals between your heartbeats are neither perfectly regular nor randomly irregular. They fluctuate with that same 1 over F signature, the time domain fingerprint of a system balanced at criticality. And a healthy heart shows more of this fractal variability, while a heart whose beats grow too regular, losing the scale-free structure, can be a heart in trouble. So the criticality is not only out there in the rock and the money and the star, observed from a safe remove. It is the beating of your heart. It is the firing of your thoughts. You are not merely a grain in the external piles. You are also, yourself, a pile, a stack of critical systems poised on the same edge, shedding small avalanches without pause and carrying, exactly like every other such system, the built-in possibility of a large one. The thing reading this is made of the very phenomenon it is reading about. I want you to feel the full weight of where that leaves you, because this is the place the whole story has been descending towards since the first sentence, and it is not comfortable, and I am not going to make it comfortable. You have spent this whole time, I suspect, picturing the pile on the table, watching the grains fall, watching the avalanches, standing safely outside it, the observer, the one who understands the system. But you were never outside it. There is no outside. The grid that runs your home is one of these systems, and you live inside it. The financial system that holds your savings and your job and your retirement is one of these systems, and you live inside it. The web of supply chains that brings you food, the international order that keeps the largest wars at bay, the climate, the biosphere itself, every one of these is a slowly driven critical system, accumulating stress toward an avalanche of a size that has no upper bound, and you do not observe these systems from a safe distance. You are a grain in every one of them. And right now, in the systems that matter most to your life, it has been quiet for a while. The grid has mostly held. The markets have mostly recovered. The great powers have mostly not gone to total war in your lifetime. And every instinct you have tells you that the quiet is safety, that the long stretch without catastrophe means the danger has passed. The mathematics says the exact opposite. And this is the single most important thing I can leave you with. In a self-organized critical system, the quiet is not the absence of catastrophe. The quiet is the catastrophe accumulating. Every year that the fault does not slip is another year of strain loaded into the rock. Every year the forest does not burn is another year of fuel piling on the floor. Every year the small corrections are smoothed over is another layer of leverage and connection wound into the system. The calm and the catastrophe are not opposites. The calm is the disaster being built. The longer the stillness lasts, the larger the avalanche that the stillness is preparing, and the more certain it becomes, not less. You have been taught to read a long piece as a sign of strength. It is, more often, the sound of a pile growing tall. I keep using the word certain, and I want to be exact about what is certain and what is not, because the precise shape of what the mathematics knows and refuses to know is the strangest part of all of this. And it is the part that does something to a person once they really absorb it. The power law is, in its own domain, almost obscenely confident. It will tell you, for a given fault system over a given century, roughly how many magnitude 7s to expect, and how many 6s, and how many 5s, and the long-run numbers come out with a steadiness that is genuinely eerie, as if the Earth were keeping a ledger. It will tell you that over a long enough stretch of financial history, crashes of a certain depth arrive with a certain frequency, and the count holds up across decades and across countries. It will tell you that wars of a given magnitude recur at a given rate across the centuries. The distribution is knowable. The distribution is, in a sense, the most knowable thing about these systems, more reliable than almost any individual fact you could name about them. If you ask the mathematics how often, over the long run, it answers without hesitating. And then you ask it the only question you actually care about, the human question, the question you would trade all the others to have answered, which is when. When is the big one? When does my fault slip, my market break, my grid fail, my world go to war? And the mathematics, which a moment ago was so confident, goes silent. Not silent because it has not finished the calculation. Silent because there is no calculation. The when is not hidden from you by a lack of data, or a lack of instruments, or a lack of cleverness. The when does not exist yet. It is not a fact about the present that you are failing to read. It is a fact about the future, that the system itself has not decided, and will not decide until the avalanche is already running, until the fault is already breaking, until the cascade is already crossing the grid. You are not being denied an answer. You are demanding an answer to a question that has no answer at the moment you are asking it. This is why every authority you might turn to abandons you at exactly the same place. And it is worth seeing that the abandonment is universal and honest rather than a failure of any one field. The seismologist can hand you the hazard map and the recurrent statistics, and will tell you plainly, if you press, that no one can tell you the date. And Parkfield is why. The economist can show you the long-run frequency of crashes, and will tell you, if honest, that the precise timing of the next one is not forecastable. And the Nobel laureates who thought otherwise are why. The risk manager can compute the distribution and will admit, in private, that the tail is exactly where the models are weakest and the timing is exactly what cannot be priced. Sornet will tell you he can sometimes narrow the window, and even Sornet is talking about a window of heightened probability, not a date, and even that is contested. Every one of them can give you the distribution. Not one of them can give you the day. They are not hiding it from you. They are standing at the same edge you are standing at, looking into the same fog. And the fog is not ignorance. The fog is the structure of reality. And here is what that does to a person, because I have spent an unreasonable amount of time with this material, and I can tell you what it does. We are not built to live inside a distribution. We are built to live inside a story, with a beginning and a cause and a warning and a date. We want the catastrophe to have a reason we could have seen, a villain we could have stopped, a moment we could have caught. Because a catastrophe with a cause is a catastrophe we could in principle prevent. And a catastrophe we could prevent is one we do not have to simply live above, the way you live above a fault. What the mathematics takes from you is not safety. You never had safety. What it takes from you is the story. It tells you that when the big one comes, and it is coming, there will be a search for the cause, and they will find a trigger, a sagging line, a failed bank, an assassinated official, and they will tell you that was the cause, and they will be wrong. In the same way they would be wrong to blame the single grain of sand. The trigger will be ordinary. It will be indistinguishable from 10,000 triggers that came before it and did nothing. The cause will not be the trigger. The cause will be that the pile was full, and the pile is always, eventually, full, and no one can tell you which grain. So we are left finally with the thing the brief I built this from named at the very start, the sentence that survives everything. That survives Bak's overreach, and the rice, and the statisticians, and the whole long argument between the pile and the dragon. The math does not predict when. It guarantees the distribution. Those are not two halves of one answer. They are the answer and the refusal, fused together, and you have to hold both at once. And holding both at once is the actual content of understanding this. There will be a magnitude 9 that no one saw coming, not because no one was watching, but because it could not be seen. There will be a crash that makes the worst one in living memory look like a correction. And afterward, there will be 1,000 explanations of why it was obvious, and every one of them will be a story told about a grain. There will be, somewhere out on the long flat line that Richardson drew, a war larger than the largest we have had, because the line does not stop and nothing in the mathematics caps it. None of these are predictions in the sense you want. All of them are guaranteed in the sense you cannot use. That is the whole of it. The distribution is destiny. The timing is free. I want to come back to Per Bak now, the way I promised in the beginning, when I told you he died at 54 and left it there, because his ending belongs in this story and not as a sad footnote. It belongs because of what he died of. He was abrasive to the very end. The people who knew him in his last years described a man who never softened his conviction that he had found something enormous, who went on insisting that nature works through self-organized criticality, long after the field had filed away his grandest claims as overreach, who fought for the idea the way he had always fought, without diplomacy and without much patience for people who understood zero, and he meant zero, of what he was saying. He moved to Imperial College London in 2000. Near the end, he had married a physicist, Maya Paksuski, who had collaborated with him on some of the work. And in 2001, he was diagnosed with myelodysplastic syndrome. And on the 16th of October, 2002, he died of it at 54 years old. Myelodysplastic syndrome is a cancer of the bone marrow. It is, when you look at what it actually is, a cascading failure in the system that makes your blood. The marrow's blood-forming cells begin to malfunction, and the malfunction propagates through the populations of cells, and the system that has quietly produced healthy blood your entire life, day after day, decade after decade, with no characteristic event and no drama, tips past a threshold and begins to fail in a way that spreads and accelerates and cannot be stopped. The man who spent his life telling anyone who would listen that catastrophe is not an outside force but an internal inevitability, that the large failure is built into the slow, ordinary functioning of the system and waits in it like a held breath, that the trigger is never the cause, and the cause is always the accumulated state, died of a disease that is, in its mechanism, the thing he described, a long quiet accumulation, a threshold crossed, a cascade. He would have seen it. I have no doubt at all that he saw it. And he died without the total vindication he wanted, which is its own small instance of the pattern he loved. The version of his idea that survived is not the version he fought for. He wanted the master key, the one law underneath the tree on fire, and the person with the flu, and the galaxy and the gene, and the trader, and he did not get it, because the rice and the statisticians took the universal claim away from him and left him with something smaller and harder and true. The outsider was right about the deep thing and wrong about how far it reached. And the establishment that resisted his overreach was right to resist it and wrong to think the resistance disposed of the core. And the core sat there through all of it, unbothered, the way the line sits there, unbothered, through every argument anyone has ever had about it. He has 53,000 citations and no monument. The idea works. It just does not work the way he needed it to, which is the most human thing about it. So here is where I have to leave you, and I am not going to make it okay, because the entire point of everything I have told you is that it cannot be made okay. And any version of this that ends in comfort is the bell curve all over again. The convenient model chosen because the true one is hard to live with. There is a single straight line that contains the worst things that have ever happened to the human species. And now you have seen it, and you cannot unsee it. The Lisbon earthquake and the crash of 1987, and the blackout of 2003, and the Second World War are on it. And so is the next one, the one with no date, the one whose trigger is being manufactured right now somewhere ordinary. A hot afternoon, a sagging wire, a clever bet, a quarrel, a single cell, a grain of sand falling onto a pile that has been growing taller and more connected and more optimized and more quiet for longer than anyone watching it has been alive. The line guarantees that the grain is in there. It guarantees how the sizes are distributed and roughly how often the large ones come over the long sweep of time. It will not, because it cannot, because the answer is not yet real, tell you which grain or which afternoon or which year. The pile does not care whether you believe any of this. It is not watching you, and it does not need your attention, and it has no opinion about whether the people who study it are vindicated. It is just being built, one ordinary grain at a time, the way it has always been built right now in the grid and the markets and the forests and the fault lines and the fragile interlocked machinery of the only civilization you have. And somewhere in it, indistinguishable from all the others, identical in every way you could measure, sitting in a place you will never be able to point to until long after it no longer matters, is the grain. It looks like all the others. It is already falling.